All right, so this is the last section that we're going to go over in chapter 4. Remember we already did 4-6 the beginning. We started with that one. That was all about compositions and inverses. Your homework on those, I think, is due Thursday. So you should have already watched it or done that homework. So now if you're watching this on time, it's Monday, July 26th. This is not on exam 3 because exam 3 is tomorrow. Had to move some questions around because this section is actually really important and it's really cool. So it kind of brings together the point of why we're bringing up logarithmic functions after exponential, because there's only so many things we could do with an exponential function, right? So remember exponential functions or an exponential equation. So function, I would plug something in and I would get an output. There's an X and a Y. An equation, I have one variable and I'm trying to solve for it. And an expression, there's no equal to sign, right? So this is an equation. So we're gonna have something like 2x to the x equals 9, right? So linear equations, we can just add or subtract each side and then divide by a number and we can solve for x. But to solve for these, we need to get this x out of the exponent. I think to think of x right here as like being otherworldly, like he's up in the clouds, he's doing his own little thing, but I need to bring him back to earth because I need to talk to him and figure out what he equals, okay? So we got to bring x back down. So we need to get the variable out of this exponent. So what function has such a property? Logarithms. Remember in your law of logs, we talked about how if I take a logarithm of something to a power, that power becomes a coefficient. It brings it down out front. And this can happen with any logarithm. It's not just a certain base. So I can, what I say is ln both sides. So you can, or log both sides. So you would do like ln 2x equals ln of 9. So I logged to g both sides. What we do to one side, we have to do to the other, right? Well, then I apply the third law, called law of logs, and that says that the exponent needs to come out front. So that will give me x times ln of 2 equal to ln of 9. And remember, ln of 2 and ln of 9 are just asking questions of what can I raise e to get to 2 or to get to 9. And that has a value. That's a number. These are just numbers. Like if like 3 or like 3.62 or 9, like they're just numbers. They have values. I don't exactly know what they are quite yet. I can plug them into my calculator and I'll get something out. But if I have like ln of y, I don't know what y is. So these are just numbers. So I can treat them as that. So I want to get x alone. So I'm going to divide by ln of 2. And you don't have to choose ln, whatever logarithm of your choice. I like ln because it's easy for me to write. If you've gained anything from the semester, it's how lazy I am with writing. Just don't tell my research advisor because I still haven't written my proposal. So now we have ln of 9 equal to ln over ln of 2. And we can actually run over to our calculator. It's on my phone. And ln 9 close parentheses divided by ln 2 close parentheses. So that's what it looks like on my phone, ln 9 divided by ln 2. And I do not have an iPhone, no one come for me. So that's going to be, when we do approximations, we're like a squiggly equals, so like it's kind of equal, but like squiggly. So like 3.1699. I don't feel like rounding, but like 3167. I'd rather have this as my solution I'd like that instead of you going from here to here, because I don't know how you got here. That's what I mean by like showing all your work. Because like, what if you plugged something in wrong to your calculator, but you got to this part correctly? I don't know that though. So it's kind of like a fail safe of like, you just plugged in something into your calculator wrong. Let's say you did ln of 9 divided by 2. You divided and wrong in your calculator. Well, if you write this, I know what you mean, right? I'd probably be like, oh, you had a calculator. So just leave it like this, and then you don't need to simplify, okay? So this whole section is about solving for x when it's in the exponent, and then we'll do sums where it's in the logarithm, and that's where inverses come into play. It's super cool. All right, so we can go a little step further. So given that 5 times 2 to the x equals 36, solve for x. So we just had 2 to the x equals 9, and we ln'd both sides, but now I have this 5 involved. It's in front. The third law says that log of, what was it? A to the x equals x times log of a. It doesn't say anything about log of b times a to the x. But then we know if things are multiplied in here, I could do it. But I think that's a little confusing, in my opinion. There's lots of ways to do it. So let's get it so it's easier to apply, move things around, and then apply a log. But then I'll show you how we can do it another way, okay? So what I would want to do is I want to do 2 to the x equals 36 divided by 5, right? So we divide by 5. And then we can log sides. So we'll have ln of 2x. You can do whatever log you want. Log bases are usually whole numbers, just like radicals are. So I wouldn't do like log base 36 over 5. And it has to be the log on both sides, right? They need to be the same thing. Ln of 36 over 5. Great. And then we know that the third law says that this x comes down. And I can solve for x by dividing by ln of 2, because that's the only thing that's kind of standing in my way. So I get ln of 36 divided by 5 over ln of 2. Beautiful. What I could have also done is just apply ln on the both sides first. Ln 5 times 2 to the x equals ln of 36. But the tricky part about this is you might bring that x down and make a mistake. So that's why I like to do it the first way, because it kind of reduces the amount of mistakes that we can make. So the first law of logs says that I can separate these two things because they're multiplied. So I can expand. That's why we had the whole expand and contract thing. And do something like this. ln of 2 to the x equals ln of 36. And it would work the same way, right? So then I would get ln 2 to the x equals ln of 36 minus ln of 5. And then we could, if we wanted to, compress that. And we can see that we're basically right here. And then I would go through the same. Okay, so that's how I can start a different way and get back to the same exact point. And you can see up here, because of the division, the second law says I can separate them, expand the logarithm, and separate them with a subtraction because it's division. Okay. That's just like I like to do rather the first way, because what if I forgot that I couldn't bring the x down, and then I'd bring it out front, and then my whole answer would be wrong. So just be weary and figure out what works best for you. Okay, great. So now we're on to 8 to the x equal to 5, 12 times 3 to the x. So in linear solving linear equations and sometimes quadratics, we want to get everything that has x involved on the one side and everything that doesn't have x involved onto the other side. So let's see if that idea of isolating x still works, right? So I'm going to divide each side by 3 to the x. So this will give me 8 to the x over 3 to the x equals 512. I really only want something to the x, just one thing. So we know from exponents that things are multiplied and divided by each other. I can pull that exponent out. So this would be like 8/3 to the x equals 512. So this is no different than the first example that we worked to, not the one before this, but the one before that. A number to the x equals another number. Okay, so we put x's on the, put things with x onto one side. All right, and now we're going to log both sides. So I'm going to ln, let's do a different log. So like log 8/3 to the x and log 512. Oopsies. And then we'll have x come down from the third law, 8/3. This hasn't changed. Oh my goodness, I don't know why I keep writing 15. And then x would be log 512 divided by log 8/3. Okay. Let me box my answers. I haven't been doing that. So this one was a little different from the one before because we didn't have everything with x onto one side. So to do that, we need to divide 3 to the x over. And great, now I have something to the x equals to another something. I know how to solve that. Apply my log, bring the exponent down to become a coefficient using the third law of logs, and so on. Okay. So sometimes we can even use properties of logarithms to help simplify problems. So you haven't seen me expand or compress or combine logarithms so much yet. So I like to use ln a lot, but sometimes we could have done log base 2 earlier. We could have done log base 10 like we did last time on another problem, but sometimes it could be easier to write to choose a specific logarithm. Remember, we want our base to be a whole number. Log base 5/3 is not, I don't think that's going to be, you're going to get, it's going to be hard. Okay. So to solve E 3 minus 2x equals 4, remember that ln of whatever is the same as log base E, right? Those are just placeholders for what's going on inside. So properties of logarithms, they're inverses of exponentials. Those are the properties that we're talking about other than the third law. That's very helpful. So since I have E as my base to my exponential, I'm going to make E the base of my logarithm. And I know I said something about keeping it whole numbers, and E is absolutely not a whole number, but just bear with me. So if I ln both sides, so I have E to 3 minus 2x equals ln of 4. 3 minus 2x is going to come down, 3 minus 2x. And then I'm going to have ln of E equals ln of 4. Well, ln of E says, what can I raise E to get to E? Just 1. So I chose that logarithm specifically to kind of, so that it would be 1. So then I would just have 3 minus 2x equals ln of 4. Remember, ln of 4 is just a number. So now we're kind of just solving a linear equation right now. So I can do, what am I going to do? Subtract 3, so I get 2x equals ln of 4 minus 3, and then divide -2. What I just thought about that I'm like so excited about? Halloween. I know it's July. I'm just so excited. And then I can do, this would be like, usually we like our negatives up top. Something like that. Okay. If I chose log base 10, I would also have log base 10 of e floating around somewhere. Probably around the log base 4. So you can see it made my life a lot easier to not even have to worry about that and solve for x. So that's how we can kind of be purposeful about choosing which ln. Okay. Try it out with a different, try it out with log base 10 and see how grosser it gets. Okay. All right, so we can do a similar method of solving equations with logarithms. So I apply a log to an exponential function, or sorry, equation. I want to be purposeful about what I'm saying, because I know it's going to bring down that exponent. But what if I have, that has x in it, but what if I have x in a logarithm? How can I get rid of that? Well, so we just used above the fact that like log base a of a to the x is going to give me x. That's one of the inverse functions, but we also have a log base a of x equals x, right? So we have both of these in our arsenal. We just used this one, so now we're going to use this one, okay? So I have ln log base e x plus 1 plus ln of 5 equal to 1. Again, we want to isolate our x before we do an e or an l log something, right? So things that have x in it stays on one side, things that don't have x in it go to the other side. So I'm going to subtract ln of 5. So we have ln of x plus 1 equals 1 minus ln of 5, right? So isolate x, isolate x. Now I'm going to e both sides, right? I have something like this, and I'm going to raise it, make it the exponent of e right here so that I get this back out. Okay, so I would draw like a little e right here and a little e under, kind of like there, just to show that I'm doing something like this. E to the ln of x plus 1 equals e to the 1 minus ln of 5. And the reason, again, that we isolate x first, and so I don't have to do this math game of like what's going on with like separating a base because the exponents are being added. If you're not that comfortable with exponent rules yet, that's why it's kind of good to do this first. All right, so inverse, this says that basically they kind of like cancel out in a sense, and x plus 1 like floats to the ground. So I'm just gonna have like x plus 1, because that was the whole point. I wanted to get x plus 1 out of the logarithm, so I raised it to the e. So if it didn't just come out, I probably did something wrong. All right, and this is going to be e to the 1 minus ln of 5. So x would equal e to the 1 minus ln of 5 minus 1. Okay. Sorry. Okay. And that's it. I know it looks kind of wonky, but it looks great. You could plug into x up here and see if you get the same thing out. And I think you would, because it would be that minus 1 plus 1 would cancel out. So you would have ln of e to the 1 minus ln of 5. And then the e and the ln would cancel out. You would just get 1 minus ln of 5. ln of 5 would cancel out, and you would have gotten 1, which is what you would want. So all right, now what if I have two things that have X involved, right? Kind of working the same way we did last time. What if I just have one X? Okay, now I have two different X's. I can't subtract log of X onto the other side and work the problem the same way, because I would just have like an ln of a log base X over there. So that wouldn't be very useful. And also I wouldn't be solving anything because my answer would have itself in it. That's called implicit. And it's not a very good answer. So this is where I can use log properties to combine things. So this is actually supposed to be a minus sign. I'm glad I checked. I think I gave this to my students last time and they were like, we can't figure it out. I was like, I don't know. So that should be a minus sign. So let's combine logs, right? This is why we kind of went through that whole section of law of logs. Yes, I get it. I can do this and I can do this, but like, what's the point? All right, so I realized watching back in the video that this didn't show up. So we're gonna redo this problem. Because I think it's really important that you guys are able to do these types of problems. I can't expect you to know how to do them on your own quite yet. All right. So I have log X plus 1 minus log X. So this should be like a minus, get rid of that, equal to 2, right? So we saw in the example before this, I want to combine my logarithms, right? Or no, I just had one X in a logarithm. Now I have two logs that each have an X in it. So and I think for 2, we learned how to expand and combine logarithms. So let's combine them, make them into one logarithm, because that's how I can knock it out with an exponential really easily. So if I have log X plus 1 and this subtraction, so it's going to be division equal to 2. Now I can raise it to a specific number to cancel out that log. So remember, if there's no base on that log, it's log base 10. So we're going to raise each side to be in 10's exponent. So this is going to give me 10 to the log X plus 1 over X and 10 squared, which will just give me X plus 1 over X equal to, because we think those are canceling out, 10 squared. We know that's just 100. So now we're just solving, not really a linear equation, but we know how to solve something like this, right? So we multiply X on both sides. So I want X plus 1 equal to 100X, subtract X, 100X minus 1X is 99X's. And I want to get X equals, so I divide by 99 and I get X equal to 1 over 99. Okay. You could have done it with E if you wanted to, would have taken a little longer. You would have had a little more numbers moving on. I think 1 divided by 99 is a very nice looking answer. So that's how we can think about it, right? And then again, we can go back and plug in X and see if we get 2 back out. Okay, so I think someone had to get comfortable on the couch. That's it. And then you guys were able to see what was happening down here when I had it. Okay, so I just wanted to go over that problem because it did not record the first time. All right. About these like investment things, continuously combated this many times a year. We only know how to go one way, right? Plug in how many years it's been, how much money do I have? Well, now I could ask the question, oh, how long will it take for me to get to this specific amount? Okay. I need to go do something really fast. I will be right back. All right, we're back. So if Helen invests $10,000 in a high yield uninsured certificate, don't know why we need to know all of that, of deposit, that pays 12% interest annually, compounded every 6 months. All right, so that's twice a year. So find a formula for the amount A of the certificate after T years. So remember that we have, for things that are not compounded continuously, this is our equation, right? So AT equaled P, which is our principal amount, our starting amount, times 1 plus R over N and T. And this will give us our annual rate and so on, right? So N is the number of times and R is our rate. So R here is 12%, but we don't plug in percentages, we plug in decimals. And since it every 6 months, that means twice a year. And P, we were told that we are investing 10,000. So I have A of T equals 10,000. 1 plus 0.12 divided by 2 to the 2T. And I can, if I wanted to, make this a little easier on myself. 10,000, 1 plus should be like 1.06 to the 2T, right? Sometimes you'll have, when things are like divided by like 365, it'll be like 1.000345. Keep it all the way out, or else you're just going to have 1 and your answers are going to be completely skewed. So really carry out that decimal. Okay. All right. So that is our formula. So what is the amount after 3 years? We all know how to do this. We're just going to plug in 3 because that's what T is, years. So I'll get 10,000, 1.06, 2 times 3, which will give me 6. So it'll be like 10,000, 1.06 to the 6. And then that'll be 1.06 raised to the 6 power, 10,000. 1.4185. I usually do 4 decimals that aren't zeros. So times 10,000 will give us 14,185.19. We put a $sign up front if we wanted to. All right. That's a decimal, not a comma. Okay, cool. So that's how much is going to be after 3 years. How long will it take for her investment to grow to 25,000? All right. So I'm not plugging in 25,000. That's a dollar amount. So I want to know when A of T equals this much. Okay. Oops, I forgot a 0. So this is going to work similar to how we've been doing the other ones when the thing we want to solve for, T, right? Because it's how long will it take. That's asking for a time. And that's stuck up in the exponent. So let's first get things that just have T involved on to one side. So this 10,000 doesn't have anything with T. So I'm going to divide it over. So we have 10,000 divided by 10,000. All these zeros cross out. And I think we just get 2.5 equal to 1.06 to the 2T. And which logarithm should we choose? Let's do ln. So we're going to ln both sides. So that's going to give me ln of 2.5 equal to ln of 1.06 to the 2T. The third law of logs says that I can bring that down. So I'll have 2T. Actually, I don't want to put that in the parentheses. 2T ln of 1.06. And then I just want T. So I'm going to divide by 2 ln of 1.06. Okay, so I would get T ln of 2.5 to ln of 1.06. And that'll approximately be 7.863, okay, years. And that makes sense because if it took me 3 years to make 14, it should take longer than that to get to 25. And then we can go back in and plug this decimal in for here. A lot of the times when I see people do these problems, I see them put like 8. And then they'll check and be like, look, I plugged in 8 and I got like 30,000. I'm like, you just show me that your answer was wrong. I want to know the time that I get exactly that amount. Okay. Not when I pass that amount. Because sure, say 100 years, like whatever, but that's not what I'm looking for. Okay. So, okay, great. All right. So we want to, make sure that we're giving it an exact answer, not rounding it so much that our answer is wrong, like saying like 8 years. That's not going to work. Okay. So another cool thing, we can also find stuff about half-life. How much is this our last problem? Okay, cool. This is our last one. Great. So tissue samples from Eisman indicate that his body had 57.67 of the carbon-4 that is present in a living person. So here you and I are, right? And we have 100% of our C14. Okay. Here is Iceman. It's pretty icy. And he has 57.67% of his C14. So he's pretty depleted. He's missing some of it, okay? So use the fact that half-life of carbon is 5,730 years to estimate how long ago the Iceman died. So we know how to model half-life. Remember, that means that I'm losing 50% every that amount of years, right? So a lot of things are going on at once. This problem is kind of like a lot of different things happening. So, but we also know half-life is kind of like a continuous thing. And I think in 4.4, we even talked about instantaneous growth rate, right? And that we can use half-life the same way. So we're going to use the model A of t equals CE to the RT, okay? Now I don't know what C is, but I don't actually need to know it, which is pretty cool. So I know that at A of how many years is at our first half-life, we're going to have half of what we started with. If we start with C, I'm only going to have half of that left, right? And then if I continue on to another half-life, I had C over 4 and so on. So I can use that and say, oh, C over 2, that's going to be C E to the R, and then T is that amount. I'm basically just writing out what A of 5730 is. 730. And now I can find R, right? So if I divide both sides by C, the C's actually cancel out. So I'd get 1/2 equals E to the 5730 R. We're gonna get ln to be 1/2 ln E to the 5730 R. So we know this is going to be 5730 R equal to ln of 1/2. So R is going to equal ln of 1/2 5730, right? So that's our R. We still don't need to know our C, right? Because we're told that he had that percentage of what he started with left over. So just like we did 1/2 or like 0.5 times C, we're going to do like 0.5767. Okay. So we see that he's not quite halfway there yet. So we really don't want an answer on a time that's going to put us past the first half-life, because that's not going to make sense. How can I have more than half if I've already gone past one half-life? So with that R, we can say that A of T equals CE to the ln of 1/2 over 570 T. And then I can set this equal to 0.57 C. So what I'm doing here is saying that he had that much percent of what he started with, right? So half-life is that's 50%. I just did over 2, it was like 1/2, but I could have done 0.5. That's the same. Okay, so that's how I went from 57.67% of what he started with. So it doesn't matter what we started with, because I'm told how much percentage I had already, right? So the C's cancel out, and we're going to ln both sides. So we'd have 5767 e to the ln of 1/2 over 5730 T ln both sides. So I have ln of 0.5767 ln of 1/2, because the E would go away, 57 30 times T, and I'm solving for T. So I'm going to multiply each side by 5730 divided by ln of 1/2. So I get 5730 ln of 0.5767 over ln of 1/2. So after plugging that into your calculator, you should see that we will get approximately, actually, I have it written out, but I want to know the decimals. So 5730 times ln, oops, 0.5767 divided by ln 0.5 gives me 4,550.23 years. Okay, and that logically makes sense right now, since he hasn't lost 50% yet. He's at 57.67%. So he hasn't gotten to a full half-life yet. So we shouldn't have passed 5,730 years yet. All right. So there's other ways to do this problem, but I kind of like to just stick with a base of E with R to the T. But I want to solve for T, but I'm missing lots of things that's going on. I don't really care about C, since I'm told half-life, I'm told a percentage, 50%. This I'm also told percentage. So I don't actually need C at all. That's totally fine. I could even make it 1 if I wanted to. R for being 100%. We don't know R, and then we're eventually going to solve for T. So we want to find R. So I plug in for, I know this amount because I know that its half-life is that many years. So that tells me this automatically. That's what this means. I'm C over 2, so 50% of my C happens when T is 5,730. Then I just plug that in right here, right? And the only thing unknown, my C's cancel out, we saw that. And so my only unknown is my R. So I work out and solve for my R. Really great. And then I can scooch down here and kind of do the same thing as half-life, but now I'm just solving for T rather than R, but they're kind of in the same place, so the work works the same. This is one of my favorite problems. I think it's really cool because you have to solve for two different things, but you don't need to know the initial condition. Okay, so that's it for chapter 4. Our next section is on chapter 5, but it's only the first section, so it's not too bad. All right, this will be on your final. This will be like in a problem or two, because I do really like it and I think it's really useful, and I can implement it into different parts. So I can ask you to find lots of different things with, now that you have the tools to solve for X. Okay, so I'll see you guys next time.